Alright guys, welcome to 2.3.2 for pre-calculus. We're going to be talking about inverses for sine and cosine functions now, more specifically about their graphs. So this is going to be much more of a hands-on physical lesson, or it would be if you were here in person. So I'm really just going to kind of walk us through the process and kind of talk about it, and then I'll kind of show you here in a second. So let's hop over to my camera. So I have here a graph of sine. Let's see if I can focus that a little bit better. Okay, so this is our standard sine graph, right? And then I have the dashed line through y is equal to x. Now, for an inverse, that is always reflexive over this line here. So you've likely done this in the past, last year when you started just first talking about inverses. But what we can do is what's called the carbon copy method. So I'm going to trace over this very, very hard in pencil so that it'll transfer when I fold it. Now I'm going to pause this because I don't want to force you to watch me trace, but then I'll be back in a second. Okay, so it should be really, really shiny, and now when I fold it over this, I'm going to try and transfer that over. So the hard part is trying to get it on the actual line. So I can see if I can see it through paper a bit. All right, well, that's pretty good. So once I got that crease, I'm going to go in here and I'm going to really hard scrape it with my fingernail to try and transfer some of that graphite or that pencil lead over to the other side of the page. So I'm scraping it with my fingernail. I'll transfer it over. And this is something that you can do if you just want to get some paper and kind of sketch a little graph. You can get an idea of what this is going to look like and how it works. It is a really nice way to kind of visually see that transfer. So now when I unfold it, it's not super great, but I do see that image, right? So I'm going to kind of go over that right here. I might use a different color. I'll use purple so I can show that I got this, and then really close together, then I kind of go down there, follow like that. So that purple line ends up being my inverse. So this is my inverse of that function, right? Awesome, great. So now the problem is this inverse is not a function, right? Because I don't pass my vertical line test here or here, and if I think about it, this graph keeps on going right and left, means that this inverse would go up and down. So I would fail my vertical line test an infinite number of times as I go up and down, no matter where I am on this little interval here. So I have to remedy that. So how can I break this up so that I am a function? And there's two really real ways that I can do it. I could either kind of stop it, cut out that middle part, and then have that portion, and then cut out the top and the bottom there, right? That is possible, but likely not the quote-unquote best one. If I remove the top and the bottom, leave just that kind of little middle, like that little middle wiggle area, that's going to be probably my best solution here, right? Because then I just have I have one little set domain here, and one set range, it's continuous on that little interval, looks pretty nice. So that's actually the one which we're going to use. So I'm actually going to go and highlight the domain that I want, which is going to be here to here. Right? So just that region there is what I actually want to use. And I'll kind of draw a little line there to kind of signify where that's being broken, because it's not super easy to see. But there to there is what I want to keep so that it is invertible. So now the question is, well, where do those parts come from on my original graph? Well, those are going to come if I cut it off here at negative pi over 2, if I cut it off here at positive pi over 2. So if I cut my domain of my original here, then it is invertible because my inverse stays a function. So that's going to be a pretty key thing here going forward, and that's a pretty important interval for all of sine. Now we're going to do the exact same thing for cosine. Just to kind of save you time, I'm going to pause it. I will do the same thing, and then I'm going to stop when I get to the point of, hey, what's the domain and the range? But you could do the same thing for your like self if you want to pause it, draw your own, and then try and transfer it. That would be a good thing to do. All right, we'll be back in a second. All right, so here is after we have transferred that graph. So we see you get this kind of curve here. Now we're trying to say, well, now what region do I need to restrict this to make it invertible? Now I could do, these ones are going to be the kind of bottom half there or the top half, right? I could theoretically kind of try and break it up just to be different, but it's really not going to be that beneficial for us. So in general, if we have a like option of top versus bottom half, we're going to go with the top half because those are more positive values for us. So we're going to kind of try that out. So if I restrict my domain, I want it to only be that portion there. So again, let me mark off to stop there and there. So where those come from on my original graph, well, this comes from here. It's right there at the origin. And then this one actually comes from way over here at pi. So what I need to do is restrict my domain of the original to only 0 to pi, because then I get this positive highlighted interval there for my cosine. Okay. So that's the kind of big thing that we're looking at today. How do we need to restrict these domains to make sure that we are invertible? Okay. So let me hop back over to this, and we see that for sine. You're doing the same thing for cosine. And then, all right, so that's effectively it for today. Now, I just want to, as our closure, kind of talk about why we chose those particular parts. So here's kind of your domain and your range, which makes sine and cosine invertible. And that is, we use for sine between negative pi over 2 and pi over 2, which we kind of saw by looking here and saying, well, that's what gives us this nice middle value, which is pretty and connected and get the stuff which we like to use quite a bit. For cosine, we did it like this. We restricted it to 0 to pi because that gives us this nice above the x-axis value here for our inverses. Works out very nicely for us. So why that's really important is if you think about when you've done sine, cosine, tangent stuff in the past, like for right triangle trig, right? You only can use that when we're in right triangles, because let's think about, where's my unit circle? What this looks like on a unit circle, right? The sine uses the interval from here to here, right? The cosine uses the interval from here to here, right? So the place where those two things overlap is this region right here, right? From 0 to 90. So every angle that is between 0 and 90 degrees, both sine and cosine's inverses work, which is why right triangle trig is so easy for us, right? We just do the inverse sine or the inverse cosine and it gives us the angle, right? Because there's only one possible answer in this particular region. Now, once we start to go outside of that to where, hey, what if it's over here? Or what if it's down here? Now we can start to get multiple answers, right? Because now, well, I have a sine of 1/2 here, but also here, right? So that opens it up to multiple things as soon as I'm outside of this one limited region. So that is why when we start to do trigonometry outside of right triangles and angles which can be greater than like 90, we have to have some extra precautions whenever we use, especially the inverses for it. So that's just kind of the precursor here to where we're going to be kind of going in the future. So with that, here is our homework for today. We're doing 139 through 146, and I will talk to you guys next time.